Okay, class, today is September the 22nd. You should have your interactive math notebook. You are going to be taking notes on these topics, non-perfect squares and radicand, and we're going to do an introduction to exponent rules. Our first part of the topic is simplifying non-perfect squares. Please get ready to take some notes on this in your interactive math notebook on a new page. All right, so let's take a look at what happens when we have a number under the radicand that is not a perfect square. What you want to do is rewrite the radicand as a product of its largest perfect square factor. That means you're going to look at that number and figure out what perfect square I can get out of that number. And I look at 125 and I recognize that I can get out a perfect square of 25. Which would be 25 times 5, which will give you back that 125. So that 25 comes out from underneath the radicand as 5, and that 5 that's underneath the radicand that is not a perfect square, it stays. So that's why our final answer is 5 radicand 5. All right, let's try some of these on your own. I want you to go ahead and try these 4 problems. Shortly, we will see how well you do on them. So you can pause the video and start working on these 4 problems. And please make sure you show your work to the right side of your interactive math notebook. All right, here are the answers to the 4 problems that you should have completed. The first one, 72, as you can see, the greatest common factor that is a perfect square for 72 is 36. 36 comes out as a 6. The 2 stays. Next, 18, the greatest common factor for 18 that is a perfect square is 9. 9 comes out as a 3, the 2 stays. Next, 360. The greatest common factor for 360 that is a perfect square is 36. 36 comes out as a 6, the 10 stays underneath the radicand. And lastly, 24. The greatest common factor that is a perfect square for 24 is 4. 4 comes out as a 2, and the 6 stays underneath the radicand. Now again, we want to make sure that we identify the largest radicand, okay? The largest perfect square, excuse me. And that will help us to solve the problem right away in a really simple step. However, there are other ways that you can actually do this. You don't have to always find the greatest perfect square. You can find as many squares as you can, perfect squares as you can out of that number and continue working until you know you can't find any more. For example, 32. We know that the greatest perfect square, one of the perfect square that I can get out of 32 is 4. And 4 times 8 is 32. It comes out as 2 square root of 8. But guess what? There's another perfect square in 8. Remember, 4 times 2 is also 8. So I can get out another perfect square, which is going to be another 2 that comes from underneath the radicand. And so 2 times 2 is 4, and we have a remainder 2 underneath the radicand. But if we use the previous steps that we learned, which was to get the greatest or the largest perfect square factor, we could only do it in one step and we're done. Here, you know it's 16. 16 is the greatest perfect square out of 32, excuse me. So that would leave me with 4 radicand 2. All right, again, notice that both answers are the same. It's just a different way of getting to the answer. All right, go ahead and pause the video as long as you want to complete these 2 questions. I will be collecting these in class. All right, the next topic that we're going to look at is properties of exponent. Essential question, we want to write this down. How do I simplify and evaluate algebraic expressions involving integer, exponent, and square roots? That's our essential question. As we go throughout this lesson, I would like for you to go ahead and make sure that you try to answer this question. Okay. On the left side of your interactive math notebook, I would like for you to create a tree map. And we're going to be classifying these different types of properties for exponents. And notice I have 4 different categories because there are actually 4 properties that we're going to look at today. And every time we talk about these properties, guys, I would like for you to add an example at the very bottom and list at least 2 things that make this property unique. 2 things that will make this property unique. And this is going to be on the left side of our interactive math notebook. All right, so here we go. Here's our first problem. A, if you take a look at A, we know that if we want to solve A, we're going to repeat 2 3 times in red, and then we're going to repeat 2 2 times in green, right? And if you notice, they're all the same. So I'm going to multiply 2 times 2 times 2 times 2, and will give us a regular number, or we can write an exponent and say 2 to the 5th power, because they're all the same, 2 to the 5th power. All right? But there's another way that we can actually do this without writing it out in that long format. And that's how we're going to actually do B and C. So here we go. The rule that we'll use here is a rule of as long as the bases are the same, I can go ahead and add the exponents in multiplication. If you recall from before in example in letter A, we had 3 2's, then we had 2 2's. How many 2's in all do we have? 5 2's, right? So that's why the answer was 2 to the 5th power. All right, and that was a long way. But you really don't have to do it the long way like how we did A. All you have to do is make sure the base is the same. As long as the base is the same in this rule, you can go ahead and add the exponent. And that's why we know for B, the answer is 3 to the 7th power. And for C, the answer is 6 to the 9th power. Right? Is that 9 power? All right. All right, here's another set of examples. Explain why the following might be true. Take a look at A. All right. What it's saying is repeat 2 3 times in red, as you can see. And then it says repeat 3 3 times in green, as you can see. So in actuality, if we were to use the distribution property, we're saying 2 times, rearrange it around our associated property, because they're all multiplication, not distribution property. I can say 2 times 3, another 2 times a 3, another 2 times a 3, right? And all we did was rearrange it around by using the associative property. All right, we put a red times a green, a red times a green, and a red times a green, and we'll multiply it out. So in actuality, it's 6 times 6 times 6, or just 6 to the 3rd power. But basically what it's saying is there's an easy way that we can actually do this without doing the long way. And here we go. This brings us to our second rule. What this is saying is as long as the exponents are now the same, all you have to do is go ahead and multiply the base. Kind of opposite of what we did in the first rule. Okay? So you look at the exponents. They're both the same exponents. Just go ahead and multiply the 2 base and you get your answer. As you can see in B, 5 times 6 is 30. Leave the exponent. 10 times 4 is 40. Leave the exponent as 4. And as you can see, the rule written. We need to have that in our tree map. All right, the next rule that we want to talk about is a rule where a power is raised to another power. So let's take a look at A. 4 to the 2nd power, we can actually rewrite that as saying 2 to the 2nd power raised to another power. In actuality, what we're saying is repeat 2 to the 2nd power twice. So 2 to the 2nd power times 2 to the 2nd power, right, is actually 2 to the 4th power. Because if you remember from rule 1, the very first rule is when you're multiplying, as long as the bases are the same, you add the exponent, right? So notice the bases are the same here, 2 to the 2nd, 2 to the 2nd. So all you have to do is add the exponent. But there's a shortcut way of doing this without actually writing it out for A. And we're going to use the rule from below to show you that. So here's what we do. When a power is raised to another power, just multiply the 2 powers and keep your base. Notice here, 3 to the 2nd power in B raised to the 2nd power. Just multiply the 2 powers. 2 times 2 is 4. Your final answer there is 3 to the 4th power. Let's take a look at the next one. 5 to the 3rd power raised to the second power. Again, all you have to do here is multiply 3 times 2, and you get 5 to the 6th power into your final answer, instead of doing the long way like we did for A. And our very last rule that we want to talk about is a rule that is in fraction form, otherwise known as division. Now look, at A, the top part says 3 to the 4th power. So if I write out 3 to the 4th power, I write it out 3 times. And then the denominator says 3 to the 2nd power. So I write that 3 out 2 times, right? And if you recall in lower grade, you can basically cross out a numerator and a denominator that's actually the same, because they cancel each other. They zero out each other. All right? So we cancel a 3 and a 3, and another 3 and another 3. So we cancel 2 pairs of 3s. All right? And we're left with 1, 2, 3 3s. So that means we're left with 3 to the 3rd power. Right? See, that's the long way of doing this. But there's actually a short way of doing A. And that includes the rule that you see below. Here's how we do it. Next video. Next slide. On this slide, as you can see, applying the rule, you're going to take the exponents and subtract them. So I'm going to take the numerator and subtract the denominator exponents from it. So here in our part B, as you can see in part B, we have our rule where we subtract the 2 exponents and we're left with 4 to the 1st power. And then in part C, we have 5 to the 10th power and 5 to the 10th power. 10 minus 10 is 0. And if you recall, anything to the 0 power is always 1. It's always 1. All right? So when it's a division / fraction, as long as the bases are the same, you just go ahead and you will just subtract the powers and you'll arrive at your answer. All right? I'll see you in class tomorrow, and we will work on some more of these problems. Please make sure you answer these 4 questions and match them or pair them off with their correct, following the exponent rule. Make sure that they match and you have the correct answers on the right side of your interactive math notebook.